The Artemis II astronauts saw something on the far side of the moon that made them go silent for 17 minutes. When mission control finally re-established contact, the crew's voices had changed. Not dramatically, but enough that the flight director noticed. What they witnessed wasn't alien structures or ancient ruins, but something that fundamentally challenged everything we thought we knew about our closest celestial neighbor. For billions of years, the moon has kept a secret. One entire hemisphere, permanently turned away from Earth, remained completely hidden from human eyes until 1959. Think about that. We'd mapped distant galaxies, calculated the movements of planets, split the atom, but we had absolutely no idea what half of our own moon looked like. When the Soviet Lunar 3 probe finally sent back those first grainy images, scientists expected to see more of the same. The familiar face of the moon we'd been staring at for millennia, just from a different angle. What they got instead stopped them cold. The far side looked nothing like the near side, not even close. The near side of the moon is covered with dark patches we call maria, ancient lava plains that form the features we recognize as the man in the moon. These maria cover about 31% of the surface facing Earth. The far side, 1%, just 1. The rest is a battered wasteland of craters stacked on top of craters, a surface so violently scarred, it looks like something used it for target practice for billions of years. This asymmetry has haunted planetary scientists for decades. Why would two halves of the same celestial body look so radically different? It's like finding out your house has a completely different architectural style on the back that you've never seen before. Same building, same materials, wildly different appearance. But the visual differences were just the beginning. When NASA's GRAIL mission mapped the moon's gravity field in 2011, they discovered something that made the asymmetry even stranger. The far side's crust is about 20 kilometers thicker than the near side's. That's not a minor variation. That's a fundamental structural difference that suggests the two hemispheres had completely different formation histories. Here's where it gets deeply unsettling. Beneath the South Pole-Aitken basin, the largest impact crater we know of in the entire solar system, there's a mass anomaly, not a small one. This thing is 5 times larger than the big island of Hawaii, buried deep in the lunar mantle, pulling the crater floor down by more than half a mile. Scientists think it might be the metallic remains of whatever asteroid created the basin, still embedded in the moon like a bullet lodged in bone. The impact that created this basin released energy equivalent to 1 trillion atomic bombs. Not million, trillion. This happened approximately 4.25 billion years ago, when the moon was still partially molten, still settling into its final form. The violence of that collision should have distributed material relatively evenly. It didn't. When China's Chang'e-6 mission touched down in the South Pole-Aitken basin on June 1, 2024, it became the first spacecraft to retrieve samples from the far side. The robotic scoop and drill collected just under 2 kilograms of lunar soil and rock. Those samples are currently turning lunar science upside down. The Chinese team studied 108 basalt fragments from the collection, most dated to about 2.8 billion years old, which fit existing models reasonably well. But one fragment clocked in at 4.2 billion years. That single rock extended our understanding of far-side volcanic activity by over 1 billion years and raised an immediate question. Why was there volcanic activity on the far side at all? The near side had plenty of volcanic action because it's home to something called the Prosolarum creep terrain. Creep stands for potassium, rare earth elements, and phosphorus, plus heat-producing elements like thorium. This concentration of radioactive materials would have kept the near side's mantle hot enough to produce massive amounts of magma. Experiments suggest it could have generated 4 to 13 times more volcanic material than the far side. The far side doesn't have this creep concentration. Its crust is thicker, colder, and should have shut down volcanic activity much earlier. Yet there it was, a 4.2 billion-year-old basalt fragment, proof of ancient volcanism, where the models said it shouldn't exist. But the real revelation came from the norite samples. Norites are a type of rock that forms from impact melt sheets, the massive pools of liquefied rock created when something big enough hits hard enough. The Chang'e-6 norites had highly anorthite-rich plagioclase and magnesium-rich pyroxene, completely different from the Mg suite norites returned from the near side. They also contained abundant iron-nickel metals with meteoritic nickel to cobalt ratios. That last detail is critical. Meteoritic ratios mean the metals didn't come from the moon's original composition. They came from whatever slammed into it. The South Pole-Aitken impact was so violent, so catastrophic, that it mixed asteroid material deep into the lunar crust, where it crystallized into entirely new rock types. We're essentially looking at hybrid rocks, part moon, part asteroid, frozen together in the moments after an apocalyptic collision. But the samples also revealed something unexpected about space weathering. The far side doesn't enter Earth's magnetotail, the protective magnetic bubble that occasionally shields the near side from solar radiation. This means the far side gets hammered by solar wind continuously with no breaks. The Chang'e-6 samples showed this brutal exposure in their structure. They lacked the vapor deposition layers found on near-side samples and had thinner amorphized layers, lower solar flare track densities, and different iron nanoparticle characteristics. The moon has two faces, and they've lived different lives. One side occasionally sheltered by Earth's magnetic field, pockmarked with volcanic plains, its crust relatively thin. The other side permanently exposed to the full fury of space, its surface a dense maze of overlapping craters, its crust 20 kilometers thicker. Same moon. Radically different experiences. The Artemis II crew became the first humans to see the entire far side with their own eyes in April 2026. They spent 7 hours photographing surface features, taking notes, marveling at the sheer density of impact craters. Commander Wiseman later described it as looking at geological violence frozen in time. Every crater representing a moment of catastrophic energy release, a small piece of the solar system's chaotic youth. Astronaut Koch noted something peculiar about the smaller craters. They were brighter than expected, like tiny pinpricks of light against the darker regolith. She described them as resembling a lampshade with thousands of tiny holes, each one glowing with reflected sunlight. The brightness suggested these impacts were relatively recent in geological terms, fresh enough that space weathering hadn't darkened the exposed material yet. The crew also observed the Oriental Basin, a 600-mile-wide crater that straddles the boundary between the near and far sides. This basin formed 3.8 billion years ago when something massive punched into the moon's surface, creating concentric rings of mountain ranges that ripple outward like frozen waves. From orbit, the Artemis II astronauts could trace these rings perfectly, seeing the geometry of a cosmic impact preserved across eons. But the South Pole-Aitken basin dominated their attention. At more than 1,500 miles across, it's not just the Moon's largest impact feature, it's the largest confirmed impact crater in the solar system. The floor sits 9,000 meters below the surrounding highlands, the lowest elevations anywhere on the lunar surface. Standing at the rim and looking inward would be like standing at the edge of the Grand Canyon, except the Grand Canyon could fit inside it dozens of times over. What makes the South Pole-Aitken basin terrifying isn't just its size, it's what that size represents. Whatever hit the Moon to create this crater was moving at incredible velocity, possibly tens of kilometers per second. The impact excavated material from deep within the lunar crust, potentially exposing mantle rock that had never seen the surface before. Scientists hoped the Chang'e-6 samples might include some of this primordial material, offering a window into the Moon's internal composition. The impact trajectory has been re-examined recently. The basin's outline tapers toward the south, and the topographic transition is more gradual in that direction, suggesting the impactor came from the south rather than straight down. A southward trajectory would have scattered thorium-rich and iron-rich ejecta in a specific pattern, which is exactly what orbital measurements detect southwest of the basin. This matters because it tells us about the excavation depth. Near vertical impacts dig deeper, potentially reaching mantle material 200 kilometers below the surface. Shallow angle impacts, while still devastating, don't penetrate as far. The evidence suggests the South Pole-Aitken impactor hit at maybe 30 degrees or less, like a cosmic bullet grazing the Moon's surface at hypersonic speed. Yet even a grazing impact released enough energy to fundamentally alter the Moon's structure. The basin formation occurred during a critical period in lunar evolution, when the Moon might still have been finishing its magma ocean crystallization. Imagine a world-spanning ocean of molten rock, slowly cooling and forming layers of different minerals based on their density. Now imagine an asteroid the size of a small state slamming into it. The impact would have shattered the partially solidified crust, mixed different layers together, injected foreign material deep into the interior, and sent massive pressure waves reverberating through the entire body. The Moon rang like a bell. Material ejected from the impact site would have rained down across the entire far side, burying the original crust under layers of debris. Some models suggest this debris layer is 3 to 6 miles thick in places. This could explain the crustal thickness difference. The far side didn't grow a thicker crust through normal geological processes. It got buried under ejecta from the South Pole-Aitken impact, a catastrophic moment that fundamentally reshaped one entire hemisphere. The near side, protected by being on the opposite face during the impact, retained its thinner primordial crust. But that theory raises another question. If the far side got buried under impact debris, why is it covered in craters while the near side has all those smooth maria? You'd expect the debris-covered far side to be smoother, not more cratered. The answer involves heat distribution and volcanic resurfacing. The near side, with its concentration of radioactive creep elements, stayed hotter longer. This heat allowed volcanic activity to continue for billions of years, with lava flows filling in impact basins and creating those dark maria we see from Earth. The far side, lacking this internal heat source and insulated by its thicker crust, cooled faster. Its volcanic activity shut down earlier, leaving ancient craters exposed with no lava flows to erase them. It's a story of two hemispheres diverging over geological time, shaped by a combination of catastrophic impacts, internal heat distribution, and their relationship with Earth. Because there's one more factor we haven't discussed yet: tidal locking. The same side of the moon always faces Earth because tidal forces have synchronized its rotation with its orbit. This didn't happen overnight. It took hundreds of millions of years for Earth's gravity to slow the moon's rotation until it matched its orbital period. But during that slowing, before the lock was complete, the moon was constantly being pulled and squeezed by tidal forces that generated internal heat. The near side, perpetually facing Earth, experienced the strongest tidal heating. The far side, facing away, felt less of this effect. This differential heating may have contributed to the asymmetric distribution of creep elements, the different volcanic histories, even the crustal thickness variation. The moon's two faces aren't just different because of random chance. They're different because of their fundamental relationship with Earth. And now, after billions of years of hiding, the far side is finally revealing its secrets to us. Sample by sample, measurement by measurement, each discovery adding another piece to a puzzle that keeps getting stranger. The samples that finally came back told a story that nobody expected. When China's Chang'e-6 lander touched down in the southern portion of Apollo crater on June 1st, 2024, it wasn't heading to just any random spot on the far side. Apollo crater sits inside the South Pole-Aitken basin, and the hope was that by drilling and scooping in this location, the mission might retrieve something extraordinary, material from deep within the moon. Maybe even fragments of the lunar mantle itself, thrown up by that ancient cataclysmic impact. The lander's robotic arm collected 1,935.3 grams of lunar soil and rock. Not a massive haul, but enough. The samples returned to Earth, and teams of scientists began their analysis. What they found was shocking. The Chinese team studied 108 basalt fragments from the samples. Basalt is volcanic rock formed when lava cools. By measuring the decay of radioactive isotopes trapped in these fragments, scientists could determine their age with remarkable precision. Most of the samples dated to about 2.8 billion years old. That alone was interesting. It confirmed that volcanic activity had occurred on the far side much more recently than many scientists had assumed. But one fragment stood out. One single piece of basalt formed 4.2 billion years ago. That's just 300 million years after the moon itself formed. That's ancient. Unbelievably ancient for volcanic activity. And it completely rewrites what we thought we knew about the far side's geological history. Remember, the far side was supposed to be the dead hemisphere, the cold, inactive, cratered wasteland that shut down volcanically billions of years ago, because it lacked the internal heat sources that kept the near side active. Yet here was direct evidence of volcanic activity happening on the far side when the moon was still practically newborn, during an era when the entire solar system was still settling into its current configuration. Professor Mahesh Anand from the Open University put it bluntly: the Chang'e-6 findings are turning well-established hypotheses and theories in lunar science upside down. scientists are having to re-examine assumptions that seemed solid for decades. This wasn't the first time Chang'e samples had disrupted the timeline. The earlier Chang'e-5 mission, which sampled the near side, found volcanic rocks dating to just 2 billion years ago. That extended the moon's volcanic activity by a full billion years beyond what anyone had expected. International researchers called it a fundamental change in our understanding of lunar evolution. Now the far side samples were doing it again, pushing volcanic activity back further, revealing that both hemispheres had far more complex and extended volcanic histories than the simple near-side active, far-side dead model suggested. But the volcanic rocks weren't the only surprise in those samples. The Chang'e-6 mission also brought back norite, a type of igneous rock rich in plagioclase and pyroxene. But these norites were different from any lunar samples collected before. They had highly anorthite-rich plagioclase, meaning they were loaded with calcium and aluminum. They were depleted in rare earth elements, and they contained abundant iron and nickel metals with ratios that matched meteorites, not typical lunar rocks. The grain sizes varied wildly. Some crystals were large, suggesting slow cooling. Others were small, indicating rapid cooling. The combination pointed to one conclusion. These norites didn't form from normal volcanic processes. They crystallized from an impact melt sheet. When the South Pole-Aitken impact occurred, the energy released was incomprehensible, 1 trillion times more powerful than an atomic bomb. That kind of energy doesn't just create a crater, it melts rock. Vast quantities of the lunar crust and upper mantle would have been instantly liquefied by the sheer force of the collision. This molten rock pooled in the newly formed basin, creating a temporary magma ocean within the crater itself. As that impact melt slowly cooled over thousands or millions of years, different minerals crystallized at different rates and temperatures, creating the varied textures and compositions we see in the norite samples. These rocks are frozen records of the most violent event in the moon's history, and they've been sitting there, largely undisturbed, for 4.25 billion years. That age, by the way, is another recent revelation. Chinese scientists used radiometric dating techniques to precisely determine when the South Pole-Aitken basin formed 4.25 billion years ago. Some meteorite samples suggest dates as old as 4.32 to 4.33 billion years, but the consensus is settling around that 4.25 billion year mark. This gives us something incredibly valuable, an anchor point. A precisely dated event in the early solar system that we can use to calibrate our understanding of impact rates, planetary evolution, and the timing of the late heavy bombardment, that period of intense cosmic violence that reshaped all the inner planets. The samples also revealed something peculiar about space weathering on the far side. When micrometeorites, solar wind particles, and cosmic rays bombard lunar soil, they create distinctive features. Tiny glass beads form from impact melts. Mineral surfaces develop amorphized layers where the crystal structure has been disrupted. Nanophase metallic iron particles appear. Vapor deposits accumulate. The far side samples showed all these features, but with notable differences from near side samples. The amorphized layers were thinner. Solar flare track densities were lower. There were fewer nanophase iron particles, and the ones present were larger than those found on the near side. The vapor deposition layers that appear on near side samples were completely absent. Why the difference? Earth's magnetic field. Once each lunar month, as the moon orbits Earth, The near side passes through Earth's magnetotail, the region where Earth's magnetic field streams away from the Sun. During this time, the near side is partially shielded from solar wind radiation. The far side never enters this protective bubble. It's exposed to the full brunt of solar wind every single moment of every day. This constant bombardment affects how the surface weathers. It changes the types and sizes of particles that form. It alters the chemical processes occurring in the top millimeters of lunar soil. The two hemispheres aren't just geologically different. They're weathering differently right now in real time because of their different relationships with Earth and the space environment. But perhaps the strangest finding from the South Pole-Aitken basin isn't in the samples at all. It's buried deep beneath the surface. In 2018, scientists using data from NASA's GRAIL mission discovered a massive gravitational anomaly under the basin. Something enormously dense is hiding beneath the crater floor. The mass is about 5 times larger than Hawaii's Big Island, and it's dragging the basin floor downward by more than half a mile. What is it? The leading theory is that it's the remains of the asteroid that created the basin. When that massive object slammed into the moon at tens of kilometers per second, it would have been partially vaporized and partially fragmented. But the core of the asteroid, especially if it was iron-rich like many asteroids, might have survived. That metallic core could have penetrated deep into the lunar mantle, where it remains today, embedded like a bullet in tissue. The anomaly extends to depths of more than 300 kilometers. That's a significant fraction of the moon's 1,737-kilometer radius. It's a foreign object lodged in the moon's interior, slowly sinking through the mantle over geological time. Its immense mass creating a permanent gravitational dimple that our satellites can detect from orbit. Alternative explanations exist. Maybe it's not asteroid material at all. Maybe it's a concentration of dense lunar mantle rock, iron and magnesium-rich minerals that were brought closer to the surface by the impact and have been slowly settling back down. Maybe it's upwelled material from deeper in the moon, denser layers that rose during the chaotic moments after impact. We don't know yet. The GRAIL data tells us something massive is there, but it can't tell us what it's made of. Future missions, possibly including ground-penetrating radar or seismic experiments, might answer that question. But here's where the South Pole-Aitken story gets even stranger. Scientists expected the impact to have excavated massive amounts of mantle material. Simulations suggested that a vertical impact of this scale should have punched through the crust entirely, bringing up rocks from 200 kilometers deep. The basin floor should be littered with mantle fragments, materials rich in olivine and pyroxene with compositions nothing like the crustal rocks we normally see. But that's not what observations show. The basin floor has elevated iron and titanium compared to typical highlands, yes, but it's not mantle composition. Crustal thickness maps indicate there's still about 10 kilometers of crust beneath the basin floor. The impact didn't punch through. It didn't excavate the mantle. How is that possible? One explanation is trajectory. Maybe the impact wasn't vertical. Recent analysis of the basin's shape suggests the asteroid might have come in at a low angle, around 30 degrees or less, from the south. A low-angle impact would have distributed its energy differently. Instead of drilling straight down, it would have scooped out a vast but relatively shallow crater, excavating primarily crustal material while leaving the mantle intact below. The tapering of the basin's outline supports this. The northern rim is sharper and more defined. The southern rim is more gradual, exactly what you'd expect from a projectile that came in from the south at a shallow angle. And southwest of the basin, there's a broad deposit of thorium-rich and iron-rich ejecta, consistent with material thrown in the downrange direction during an oblique impact. This ejecta field is fascinating in its own right. Thorium is one of those creep elements that should be concentrated on the near side. Finding it in abundance on the far side, specifically in the ejecta from the South Pole-Aitken impact, suggests the asteroid punched through layers of the crust that contained late-stage magma ocean liquids. The stuff that should have sunk to the bottom during the Moon's formation, but got mixed up and redistributed by this catastrophic collision. The timing matters here. The South Pole-Aitken impact happened 4.25 billion years ago. The Moon formed roughly 4.5 billion years ago. That's only a 250 million year gap. When the asteroid hit, the Moon might still have been in the final stages of magma ocean crystallization. The interior might still have been partially molten. The crust might have been thinner and more fragile than it is today. An impact during this critical window would have had effects we can barely imagine. It would have sent shockwaves through a partially solidified world, fracturing the crust, disrupting the crystallization sequence, redistributing heat-producing elements, possibly even affecting the Moon's rotation and orbital evolution. The entire far side hemisphere was reshaped in an instant, and now, over 4 billion years later, we're finally starting to piece together what happened. The samples are physical evidence, fragments of that ancient violence, preserved in airless cold, waiting for us to find them and read their story. But the Chang'e-6 samples tell us something else happened on the far side, something that left its own mark on those ancient rocks. When the Chinese team analyzed those 108 basalt fragments, they weren't just looking at volcanic rocks. They were looking at rocks that had been sitting on the lunar surface for billions of years, exposed to space. And space is not gentle. The Moon has no atmosphere, no magnetic field, nothing to shield it from the constant barrage of radiation streaming from the sun. Solar wind particles slam into the surface at hundreds of kilometers per second. Cosmic rays punch through rock at nearly the speed of light. Micrometeorites pepper the surface in an endless rain of tiny impacts. Over millions of years, these forces weather the surface in ways completely different from erosion on Earth. This is space weathering, and it leaves specific signatures in lunar rocks. On Earth, weathering means water, wind, chemical reactions. Rocks break down into soil. Minerals dissolve. The landscape softens. But on the Moon, weathering is violent and atomic. Solar wind particles implant themselves directly into the crystal structure of minerals. Radiation damages the atomic lattice. Micrometeorite impacts vaporize tiny amounts of material, creating glass coatings and nanoscale metallic particles. Scientists can read these signatures like a history book. The thickness of amorphized layers tells you how long a rock has been exposed. The density of solar flare tracks reveals radiation exposure. The size and distribution of nanophase metallic iron particles shows how much vapor deposition has occurred. Near-side samples collected by Apollo have characteristic space weathering features. Vapor deposition layers coat the surfaces. Thick amorphized zones show extensive radiation damage. High densities of solar flare tracks. Small nanophase iron particles distributed throughout. The Chang'e-6 far side samples are different. They lack the vapor deposition layers seen on near-side samples. Their amorphized layers are thinner, solar flare track densities are lower, and the nanophase metallic iron particles are fewer in number but larger in size. At first, this seems backwards. The far side should be more weathered, not less. It's exposed to the same solar radiation, the same cosmic rays, the same micrometeorite bombardment. Why would it show less weathering? The answer lies in Earth's magnetic field. Every month, the Moon passes through Earth's magnetotail. The near side enters this region during each cycle. For a few days, it's shielded from solar wind by Earth's magnetic field. The radiation environment changes. Solar wind particles can't reach the surface. Space weathering slows. The far side never enters the magnetotail. It faces away from Earth. It's never shielded. It's exposed to full solar wind radiation all the time, every day, for billions of years. This creates a paradox. More exposure should mean more weathering, but the Chang'e-6 samples show less. The explanation reveals something subtle about how space weathering works. It's not just about total exposure, it's about the type of exposure and the intensity patterns. The near side gets intermittent protection. When it's in the magnetotail, solar wind stops. When it exits, solar wind resumes. This cycling creates specific conditions for vapor deposition. Material vaporized by micrometeorite impacts can condense differently when the radiation environment fluctuates. The far side never gets that cycling, it's always exposed. The weathering processes run continuously without interruption. This creates different conditions for how vapors condense, how radiation damage accumulates, how nanophase iron forms. The larger iron particles on the far side suggest a different formation mechanism. Instead of many small particles forming from rapid condensation, fewer but larger particles grow over longer timescales. The continuous radiation allows these particles to coalesce and merge rather than being disrupted by cycling conditions. This matters for understanding lunar history. Space weathering rates affect how we date surface features. If the far side weathers differently than the near side, we can't apply the same models to both hemispheres. Age estimates based on weathering characteristics need to account for these differences. But there's something else in those Chang'e-6 samples. Something that connects back to the South Pole-Aitken impact and reveals how that ancient collision still influences the far side today. The Norite samples. Norites are igneous rocks, rich in plagioclase feldspar and pyroxene. They form when magma cools slowly enough for these minerals to crystallize. On Earth, you find norites in layered intrusions, places where magma chambers slowly solidified over thousands of years. The Apollo missions brought back norites from the near side. These samples, called MG-sweet norites, have specific compositions. Their plagioclase contains moderate amounts of rare earth elements. Their pyroxene has characteristic iron to magnesium ratios. They formed from magmas generated in the lunar mantle, rising through the crust, cooling in plutons beneath the surface. The Chang'e-6 norites are completely different. Their plagioclase is almost pure anorthite, the calcium-rich end member of the feldspar series. It's depleted in rare earth elements to levels rarely seen in lunar samples. The pyroxene is extremely magnesium-rich, more so than any near-side norites. And here's the key detail. They contain abundant iron-nickel metal grains with meteoritic nickel-to-cobalt ratios. That last part is the giveaway. Meteoritic ratios mean the metal came from an asteroid, not from lunar magma. These norites didn't form from mantle-derived melts rising through the crust. They crystallized from impact melt. When the South Pole-Aitken asteroid hit, it didn't just excavate rock, it melted it. The impact energy was so intense that it created a massive melt sheet, possibly hundreds of meters thick, covering the basin floor. This wasn't lava from volcanic eruptions. It was crustal rock and asteroid material melted together by the violence of the collision. As this melt sheet cooled, minerals crystallized. The cooling wasn't instantaneous. A melt sheet that thick would take thousands of years to solidify completely. During that time, crystals grew, settled, and formed layered structures. The Chang'e-6 norites crystallize from this melt sheet. Their unusual composition reflects the mixed source. Lunar crustal rocks melted together with asteroid material. The meteoritic metal grains are fragments of the impactor itself, dispersed through the melt. The depleted rare earth elements show that the source material was ancient crustal rock, formed early in lunar history, before rare earth elements became concentrated. Variable grain sizes and cooling rates in the samples indicate different positions within the melt sheet. Some norites have coarse crystals, suggesting slow cooling deep in the sheet. Others have finer grains, indicating faster cooling near the surface or edges. This is direct physical evidence of the South Pole-Aitken impact process. We're not just inferring what happened from models and simulations. We're holding pieces of the impact melt sheet in our hands. We can analyze the chemistry, measure the cooling rates, study the crystal textures, and reconstruct how that ancient collision transformed rock into magma and back into rock again. But the norites tell us something else. Their ages cluster around 4.2 billion years, matching the age of the basin itself. This confirms they formed directly from the impact, not from later volcanic activity. The South Pole-Aitken collision created a melt sheet massive enough that its crystallization products are still scattered across the basin floor, waiting to be sampled. The volcanic basalts in the Chang'e-6 samples have their own story. Most date to 2.8 billion years ago, but one fragment formed 4.2 billion years ago, right around the time of the impact. This 4.2 billion-year-old basalt is significant. It's the oldest far-side volcanic rock ever sampled. It extends the known volcanic history of the far side back by 1.4 billion years. And its timing, coinciding with the South Pole-Aitken impact, suggests a connection. Large impacts can trigger volcanism. The energy from the collision heats the surrounding crust and mantle. Fractures created by the impact provide pathways for magma to reach the surface. In the case of South Pole-Aitken, an impact occurring while the magma ocean was still crystallizing would have disrupted the normal sequence of solidification. Late-stage magma ocean liquids, enriched in iron and titanium, might have been mobilized by the impact. Fractures extending deep into the crust could have tapped these dense, iron-rich melts, bringing them to the surface as volcanic flows. The 4.2 billion-year-old basalt might be one of these impact-triggered eruptions. The younger basalts, dated to 2.8 billion years ago, represent a different phase of volcanism. By that time, the moon had cooled significantly. Most volcanic activity had ceased. But in the South Pole-Aitken basin, conditions were different. The basin floor sits lower than the surrounding highlands. It's closer to the mantle. The crust is thinner there, only 30 kilometers compared to 60 to 80 kilometers in the surrounding regions. This thinner crust made it easier for magma to reach the surface, even as the moon's interior cooled. Additionally, the impact might have fractured the crust deeply enough that these fractures remained open for billions of years, providing conduits for later volcanic eruptions. Radioactive decay of thorium and other heat-producing elements in the basin ejecta could have generated localized hotspots in the underlying mantle, creating pockets of melt that eventually erupted. The volcanic plains visible in the basin cover about 8% of the mapped area. They're concentrated near the center of the basin and around the Apollo crater. Their ages span from 3.8 billion years ago to 2.8 billion years ago, showing that volcanism occurred in pulses over a billion-year period. This extended volcanic activity is remarkable. The far side, as a whole, has very little volcanic coverage, only 1% compared to 31% on the near side. The South Pole-Aitken basin contains a disproportionate amount of that 1%. Why? The impact created conditions that allowed volcanism to persist longer on the far side than it could have otherwise. The deep excavation, the thin crust, the fracture networks, the redistribution of heat-producing elements all combined to keep the volcanic fires burning for over a billion years after the collision. But even with this extended activity, the volcanic plains can't explain the basin's extensive iron signature. The spectral data shows elevated iron and titanium across much of the basin floor. The volcanic plains cover only 8%. The rest of the iron signature must come from something else. The leading explanation goes back to the pre-impact crust. Before the South Pole-Aitken collision, the far side crust might have been stratified with respect to iron content. The upper layers were relatively poor in iron, dominated by anorthosite. Deeper layers contained more iron-rich minerals. When the asteroid hit at a shallow angle, it excavated primarily the upper crust to form the basin rim, ejecting the iron-poor anorthosite outward. But on the floor of the basin, the impact exposed the deeper, iron-richer crustal layers. This spatial segregation explains why the rim is bright and the floor is dark, why the highlands are iron-poor and the basin is iron-rich. This stratification itself requires explanation. How did the early lunar crust develop distinct iron-rich and iron-poor layers? The answer involves the magma ocean again. As the magma ocean crystallized, different minerals formed at different stages. Early crystallization produced olivine and pyroxene, which are denser and sank. Later crystallization produced plagioclase feldspar, which is less dense and floated to form the primordial crust. But the crystallization wasn't perfectly uniform. Local variations in temperature, pressure, and composition created pockets where iron-rich minerals crystallized alongside plagioclase. These pockets became incorporated into the lower crust as it solidified. The result was a crust with vertical compositional gradients. The uppermost layers were nearly pure anorthosite. Deeper layers contained increasing amounts of iron-rich minerals. Deepest were cumulates rich in pyroxene and olivine. The South Pole-Aitken impact stripped away the upper anorthosite layer across the basin floor, exposing the iron-enriched lower crust beneath. This exposed layer has been sitting there for 4.25 billion years, creating the iron signature we observe today. And now, with the Chang'e-6 samples, we have physical confirmation. The norites crystallized from impact melt that mixed crustal materials from different depths. The basalts erupted through fractures that tapped iron-rich source regions. The space weathering patterns reflect billions of years of exposure in a unique radiation environment. Every sample is a piece of the puzzle. Every measurement adds another constraint. The far side is revealing its secrets, one rock at a time. The far side's secrets extend beyond solid rock and frozen lava. Beneath the surface lies something that shouldn't be there. The GRAIL mission didn't just measure crustal thickness. It mapped the moon's gravitational field with unprecedented precision. Two identical spacecraft flew in formation, their separation distance measured to within microns. As they passed over mass concentrations, their spacing changed slightly. Those tiny variations revealed density anomalies hidden beneath the surface. Under the South Pole-Aitken basin, GRAIL detected a massive gravitational anomaly. Something 5 times larger than Hawaii's Big Island is pulling the basin floor downward. The excess mass is dragging the surface down by more than half a mile. It's enormous, dense, and buried deep in the mantle. What is it? The most straightforward explanation points back to the impact itself. When the asteroid struck 4.25 billion years ago, it didn't simply vaporize on contact. Parts of it survived, driven deep into the lunar interior by the collision's violence. The projectile was probably rich in iron and nickel, metals far denser than lunar crustal rock. Those metallic remnants sank through the fractured mantle and came to rest at depth, creating a permanent mass anomaly. This isn't speculation. Impact simulations show that low-angle collisions can drive significant portions of the impactor into the target body. The shallower the angle, the more likely fragments survive. The South Pole-Aitken impact hit at roughly 30 degrees, perfect conditions for implantation. But there's a problem with the simple buried asteroid explanation. The anomaly extends to depths exceeding 300 kilometers. That's deep into the mantle. For metallic fragments to reach those depths, they would have needed to sink through hundreds of kilometers of solid or partially molten rock, possible during the impact's immediate aftermath when temperatures were extreme and the mantle locally molten. But the physics gets complicated quickly. An alternative explanation involves mantle composition. Perhaps the anomaly isn't foreign material at all, but rather native lunar rock with unusual density. The impact could have excavated deep crustal layers and mixed them with upper mantle material, creating a chemically distinct zone enriched in iron-bearing minerals. Olivine and pyroxene are denser than plagioclase. Concentrate enough of them in one place, and you create a gravitational signature. The Chang'e-6 norites offer a clue. Remember their meteoritic nickel-to-cobalt ratios? Those ratios suggest the presence of extraterrestrial material mixed into the impact melt, not just trace amounts, significant concentrations, enough to affect the geochemistry of the rocks that crystallized from that melt. If meteoritic material made it into the surface rocks, larger fragments certainly reached greater depths. The norites preserve evidence of what happened at shallow levels. The gravitational anomaly reveals what happened far below. But here's where it gets stranger. The anomaly isn't centered directly under the basin's geometric center. It's offset slightly, positioned beneath the basin's deepest point, but not symmetrically. This asymmetry suggests the impactor didn't penetrate vertically. It came in at an angle, drove into the mantle at a slant, and the surviving fragments settled in an elongated zone beneath the impact site. That elongation appears in the gravity data. The anomaly isn't circular, It stretched, aligned roughly with the impact trajectory reconstructed from basin shape and ejector distribution. Everything points to a low-angle collision that implanted metallic debris in an asymmetric pattern beneath the basin floor. The mass anomaly has consequences beyond gravitational measurements. All that buried metal affects heat flow. Iron and nickel conduct heat more efficiently than silicate rock. If there's a massive metallic body beneath the basin, it could act as a thermal conduit, channeling heat from the deep interior toward the surface. This enhanced heat flow might help explain the basin's extended volcanic history. More heat reaching the base of the crust means longer-lasting melting conditions in the mantle below. The volcanic rocks themselves show evidence of high-temperature source regions. The basalts contain minerals that only crystallize from particularly hot magmas. Their compositions require mantle temperatures higher than typical lunar conditions. Where did that extra heat come from? One possibility: radioactive decay in creep-rich materials excavated and redistributed by the impact. Thorium and uranium generate heat as they decay. Concentrate enough of them in one area, and you locally warm the mantle. The thorium-rich ejector deposits southwest of the basin support this idea. If heat-producing elements were excavated from the deep crust and scattered across the basin floor, they could have sustained elevated temperatures for billions of years. Another possibility: the impact itself deposited tremendous energy into the lunar interior. That energy didn't dissipate instantly. It took time to radiate away, time measured in hundreds of millions of years. During that cooling period, the mantle beneath the basin remained hotter than surrounding regions, promoting partial melting and enabling volcanic activity long after the impact. Both mechanisms probably contributed. The impact delivered energy, redistributed heat-producing elements, and created structural pathways for magma ascent. The buried metallic anomaly enhanced heat conduction. The result was a basin uniquely suited for prolonged volcanism, despite being located on the cold, thick-crusted far side. The Artemis II astronauts saw this history written across the surface. During their flyby in April 2026, they became the first people to view the entire far side with their own eyes. For 7 hours, they photographed and documented surface features, focusing on scientifically significant targets, including the Oriental Basin and various far side craters. Their observations added a human dimension to decades of robotic data. Koch described smaller craters as surprisingly bright, like a lampshade with pinprick holes. The contrast between dark volcanic plains and bright crater rays was stark even from altitude. Wiseman noted color variations invisible in most photographs, subtle browns and greens hinting at compositional differences across the surface. But what struck them most was the far side's sheer density of impacts. Crater upon crater, overlapping in chaotic patterns that erase any sense of order. Anders had compared it to a sandpile his kids played in, beaten up with no definition. That description holds. The far side looks ancient, battered, thoroughly worked over by billions of years of bombardment. The Artemis crew's experience echoes those of the Apollo astronauts, who first saw the far side in 1968. Every human who has witnessed it directly reports the same sense of overwhelming antiquity. The far side preserves early solar system history in ways the near side cannot. Its thick crust resisted volcanic resurfacing. Its ancient craters remain largely undisturbed. It's a museum of planetary violence. The South Pole-Aitken basin dominates that museum. From orbit, It's difficult to grasp the scale. The basin spans 2,500 kilometers. Its floor lies 9,000 meters below the surrounding highlands. Mountains around the rim reach 8,500 meters in elevation, with base-to-peak heights of 7,000 meters. These are numbers comparable to terrestrial mountain ranges, but on a body 1/4 Earth's diameter. Flying over the basin in the Artemis spacecraft, the crew would have seen the gradual descent into the impact scar. The transition isn't abrupt. The basin's rim has been degraded by subsequent impacts, eroded by micrometeorite bombardment, softened by billions of years of space weathering, but the overall structure remains clear. A vast depression, darker than the surrounding highlands, interrupted by scattered patches of volcanic plains and smaller impact craters that have punched through the basin floor. One of those craters is Apollo, the Chang'e-6 landing site. From orbit, Apollo appears as a relatively fresh impact structure nested within the larger basin. Its floor is flat, filled with ancient lava flows that erupted 3.8 billion years ago. The lander touched down in the southern portion of Apollo crater, chosen for its smoothness and accessibility. The samples collected there represent a tiny fraction of the basin's total area, yet they're transforming our understanding. Professor Mahesh Anand from the Open University stated that findings from Chang'e-6 are turning well-established hypotheses upside down. Theories developed from decades of near-side samples are being challenged. The far side is revealing itself as fundamentally different, not just in appearance but in composition, history, and evolution. This shouldn't surprise us. The two hemispheres formed under different conditions. The near side faced Earth, experiencing tidal forces that may have affected its internal structure. The far side faced deep space, exposed to more intense radiation and micrometeorite bombardment. The near side received Carib-enriched materials from the Procellarum region. The far side did not. These differences accumulated over billions of years. Small initial variations became amplified through feedback processes. More heat led to more volcanism, which led to thinner crust, which led to more volcanism. Less heat led to less volcanism, which led to thicker crust, which led to less volcanism. The two hemispheres diverged, each following its own evolutionary path. The South Pole-Aitken basin sits at the intersection of these divergent histories. It formed during the final stages of magma ocean crystallization, a time when the lunar interior was still partially molten and compositionally stratified. The impact excavated materials from multiple depths, mixing them in ways that created unique compositions. It redistributed heat-producing elements, altered crustal thickness patterns, and created structural weaknesses that would influence volcanism for over 1 billion years. And beneath it all lies that mysterious mass anomaly, metallic remnants of an ancient asteroid. Dense mantle accumulates churned up by the impact, some combination of both. The gravity data alone can't answer that question. We need more information. Seismic data would help. Placing seismometers around the basin and recording moonquakes could reveal the anomaly's internal structure. Electromagnetic sounding could distinguish metallic conductors from silicate rock. Sample return from multiple locations within the basin could constrain composition and formation processes. The Artemis missions will provide some of these answers. Proposed landing sites sit on the basin's rim, on the thorium-rich ejecta deposits. Astronauts will collect samples, deploy instruments, and conduct field observations that robotic missions cannot replicate. They'll walk on terrain thrown from the deep lunar interior 4.25 billion years ago. They'll gather rocks that preserve evidence of the collision that created the solar system's largest known impact crater. But even Artemis won't solve all the mysteries. The basin is too large, too complex, too deeply modified by subsequent processes. Each sample will answer some questions while raising others. Each measurement will constrain some parameters while revealing new anomalies. This is how planetary science works. Understanding builds slowly, accumulating piece by piece. The far side is patient. It has waited 4.5 billion years to tell its story. A few more decades won't matter, but while we wait for future missions to fill in the gaps, the far side continues revealing surprises through what we've already observed. The Artemis II Flyby in April 2026 provided something no robotic probe could deliver. Human eyes witnessing the entire lunar far side for the first time in history. Christina Koch, Victor Glover, Reed Wiseman, and Jeremy Hansen spent 7 hours photographing and documenting surface features. They saw things that challenged their expectations. Koch described smaller impact craters glowing like a lampshade with pinprick holes, far brighter than the surrounding terrain. The crew reported brown and green hues on portions of the near side, colours that defied their mental image of a monochrome moon. These weren't hallucinations or instrument artifacts. Human vision perceives subtle colour variations that cameras often miss or flatten. The astronauts saw the moon as it truly appears, not filtered through sensor limitations or image processing algorithms. Their observations complement, but don't replace robotic data. They add a layer of context that pure measurement cannot capture. The Artemis II crew also experienced something unprecedented, a solar eclipse viewed from behind the moon. For 1 hour, they watched Earth block the sun while orbiting the far side. Totality revealed Mars, Venus, and Saturn alongside background stars. The sun's corona appeared as delicate wisps, baby hairs they called them, fringing the lunar disk. This unique vantage point drove home the moon's true isolation. During the eclipse, with Earth blocking the sun and the crew positioned on the far side, they were as far from home as any humans have ever travelled. They set a distance record, 252,756 miles from Earth, over 4,100 miles farther than Apollo 13's emergency trajectory in 1970. The emotional impact was profound. Koch reflected that seeing Earth from this perspective revealed how much we share, how Earth provides everything we need, how that realization can't be fully grasped until you've experienced the alternative. The far side offers that alternative. It's a place utterly unlike anywhere humans evolved to live. Space weathering shapes the two hemispheres differently. The far side receives stronger solar wind radiation because it never enters Earth's magnetotail. During each lunar month, the near side spends time shielded by Earth's magnetic field. The far side does not. This exposure leaves distinct signatures. Chang'e-6 samples show the effects. Compared to near-side materials, far-side regolith lacks vapor deposition layers. It exhibits thinner amorphized rims on individual grains. Solar flare track densities are lower. Nanophase metallic iron particles are less numerous but larger on average. These differences accumulate over billions of years. Why does this matter? Space weathering affects how we interpret remote sensing data. Spectroscopic measurements from orbit detect weathering products, not pristine compositions. Understanding the differences between near-side and far-side weathering helps us correct for these effects. It improves our ability to infer what lies beneath the regolith without drilling. The far side also offers unique opportunities for radio astronomy. Earth's electromagnetic noise, radio, television, cellular signals, everything electronic, creates constant interference for radio telescopes on Earth's surface. The Moon's far side provides natural shielding. Place a radio telescope there and Earth's noise vanishes completely. Low-frequency radio waves blocked by Earth's ionosphere could be detected from the lunar far side. These frequencies carry information about cosmic dawn, the epoch when the first stars ignited and ended the universe's dark ages. They reveal processes from the early universe that higher frequencies cannot access. China's Chang'e-4 lander, which touched down on the far side in January 2019, carried a low-frequency radio spectrograph. The Yutu-2 rover continues operating after more than 5 years, making it the longest-lived lunar rover in history. It demonstrated that sustained far-side operations are feasible with relay satellite support. The Queqiao relay satellite, launched in 2018, made Chang'e-4 possible. Positioned at the Earth-Moon L2 Lagrange point, it maintains line of sight with both Earth and the lunar far side. All communications pass through Queqiao. Without it, the lander and rover would be deaf and mute, cut off from ground control. This communication challenge defined early far-side exploration. During Apollo missions, spacecraft passing behind the Moon entered communications blackout. Astronauts were truly alone, beyond Earth's reach, dependent entirely on their training and systems. No one could help if something went wrong during those tense minutes. Harrison Schmitt, the geologist astronaut who walked on the Moon during Apollo 17, lobbied hard for a far-side landing. He wanted to explore Tsiolkovsky Crater, a lava-filled impact basin on the far side. His proposal included a dedicated relay satellite at L2. NASA rejected the plan. Too risky, too expensive, insufficient return on investment given Apollo's limited remaining flights. Schmidt's vision waited nearly 50 years to become reality. Chang'e-4 fulfilled it, demonstrating that far-side landings are operationally feasible. Artemis will expand on that foundation. Proposed landing sites sit on the rim of South Pole-Aitken basin, on thorium-rich ejecta deposits that tell the story of the impact. Future missions will target specific questions. Chang'e-7, scheduled for 2026, will survey for water ice near the South Pole. Water ice in permanently shadowed craters could support human exploration. It provides drinking water, oxygen for breathing, hydrogen, and oxygen for rocket fuel. Finding accessible ice deposits changes the economics of lunar operations. Chang'e-8, planned for 2028, will test in situ resource utilization technologies. Can we extract oxygen from lunar regolith? Can we manufacture building materials from local resources? Can we operate mining equipment remotely with Earth-Moon communication delays? These aren't academic questions. They determine whether sustained lunar presence is feasible. The far side factors into these plans because it represents half the Moon's surface and resources. Limiting exploration to the near side means ignoring vast territories. The far side's thicker crust may contain mineral deposits absent from the near side. Its reduced volcanic resurfacing preserves ancient terrains that near side Maria buried. Its unique exposure to space weathering creates different regolith characteristics that might prove valuable, but practical considerations compete with scientific ones. Communication requires relay satellites. Landing sites must balance scientific value against operational constraints. Solar power is limited near the poles where permanently shadowed craters exist, alongside peaks of eternal light. Nuclear power becomes more attractive for far-side operations, especially for facilities that need consistent power regardless of sun angle. The far side's isolation also offers advantages. Radio telescopes operate without interference. Seismometer networks detect moonquakes without contamination from human activity. Astronomy conducted from the far side achieves sensitivities impossible on Earth, or even on the near side. The Moon becomes a platform for observing the universe. These future possibilities rest on understanding what's already there. The South Pole-Aitken basin anchors that understanding. Its age, 4.25 billion years, precisely determined from Chang'e-6 samples, provides a calibration point for the entire lunar chronology. Impact basins across the solar system can now be dated relative to this anchor. The basin's composition reveals the Moon's internal structure. That mysterious mass anomaly beneath the basin floor constrains models of the lunar interior. Is the Moon's mantle homogeneous or layered? How much metal segregated into a core? What happened to dense materials that should have sunk during magma ocean crystallization? The basin's volcanic history extends our understanding of lunar thermal evolution. Volcanism occurred in South Pole-Aitken Basin from at least 4.2 billion years ago until 2.8 billion years ago, possibly later. That's over 1.4 billion years of intermittent volcanic activity. What kept the interior molten for so long? Where did the magma come from? Why did it eventually stop? The basin's impact trajectory, now recognized as southward rather than northward, changes how we interpret its structure. Ejecta deposits concentrate southwest of the basin. The thorium-rich signature there suggests excavation of late-stage magma ocean materials. The gradual topographic transition toward the south indicates an oblique impact angle, possibly as shallow as 30 degrees. This oblique impact scenario explains several puzzles. It accounts for why the basin didn't excavate deep mantle materials despite its enormous size. It explains the asymmetric distribution of ejecta. It reconciles the observed crustal thickness, about 30 kilometers beneath the basin floor, with impact models that predicted near-total crustal removal. Yet questions remain. If the impactor struck at a shallow angle, where did it come from? Orbital mechanics constrain possible trajectories. The timing during late magma ocean crystallization narrows the possibilities further. The solar system at 4.25 billion years ago was still chaotic, with planetesimals scattered throughout the inner solar system. Any of thousands of objects could have struck the Moon. We'll never identify the specific impactor. It vaporized on contact, its atoms mixing with lunar material in the impact plume. But we can characterize it. Size estimates suggest roughly 200 kilometers diameter. Composition was probably chondritic, similar to asteroids. Velocity was lower than typical impacts, consistent with an object in a similar orbit to the Moon. The energy released was staggering, 1 trillion times greater than an atomic bomb explosion. For comparison, the Chicxulub impact that killed the dinosaurs released about 100 million megatons. The South Pole-Aitken impact released energy equivalent to roughly 100 billion megatons. The moon rang like a bell for months afterward. That energy didn't just create a crater, it reset the moon's thermal state in the impact region. Rock melted to depths of dozens of kilometers. The melt sheet took millions of years to solidify. As it cooled, minerals crystallized in sequence, creating layered rocks that preserve the chemical evolution of the cooling magma. Chang'e-6 returned norite samples crystallized from this impact melt. Their composition differs from norites collected on the near side. They contain highly anorthitic plagioclase, rare earth element pore compared to typical lunar rocks. They're rich in magnesium-bearing pyroxene, abundant iron-nickel metal particles with meteoritic nickel-to-cobalt ratios dot the samples. These characteristics point to impact origin. The metal particles came from the impactor. The plagioclase composition reflects rapid crystallization from superheated melt. The rare earth depletion indicates minimal contamination from creep-rich materials. The South Pole-Aitken impact created a massive magma chamber that evolved independently from the near side's volcanic systems. Variable grain sizes and cooling rates within the norite samples reveal complex thermal histories. Some portions cooled quickly near the melt sheet's surface. Others cooled slowly at depth. Subsequent impacts mixed these materials, creating the heterogeneous samples that Chang'e-6 collected 4.25 billion years later. The iron signature that dominates South Pole-Aitken Basin's spectroscopic appearance has puzzled scientists since its discovery. The basin floor shows elevated iron and titanium compared to surrounding highlands. Yet volcanic plains cover only 8% of the basin's interior. Where does the iron signature come from? New analysis suggests the signature predated the basin. The lunar crust may have been stratified with respect to iron concentration. The upper crust contained less iron. The lower crust contained more. The South Pole-Aitken impact excavated the iron-poor upper crust, piling it into the basin rim. It exposed the iron-rich lower crust on the basin floor. This stratification would have formed during primordial crust formation. As the magma ocean crystallized, plagioclase floated to form the crust. But plagioclase chemistry varied with depth. Early crystallization produced iron-poor plagioclase. Later crystallization from more evolved magma produced iron-richer plagioclase. The result, a compositionally layered crust. The South Pole-Aitken impact sampled this stratification, revealing structure that would otherwise remain hidden. We're literally looking at the moon's geological cross-section, exposed by the violence of ancient collision. This stratified crust theory solves multiple puzzles simultaneously. Why does South Pole-Aitken show elevated iron without extensive volcanic cover? The impact exposed deeper, iron-rich layers. Why do spectroscopic measurements show such stark compositional differences between basin floor and rim? They're sampling different crustal depths. Why has this signature persisted for over 4 billion years? It's not a surface coating that erosion could remove. It's the fundamental composition of exposed crustal layers. But crustal stratification raises its own questions. How did the primordial crust develop layered chemistry? The answer returns us to the magma ocean, that global molten shell that dominated the moon's first 100 million years. As the magma ocean cooled, minerals crystallized in sequence based on their melting temperatures. Olivine and pyroxene formed first, sinking through the liquid. Plagioclase formed later, but it was less dense than the surrounding magma. It floated upward, accumulating at the surface to create the primordial crust. This process wasn't instantaneous. It took millions of years. During that time, the chemistry of the remaining magma evolved. Early plagioclasic crystals formed from relatively primitive magma. Later crystals formed from more evolved, iron-enriched liquid. The result: progressive chemical stratification within the growing crust. The deepest crustal layers contain plagioclase that crystallized early, when the magma ocean was hotter and less evolved chemically. The upper crustal layers contain plagioclase from later crystallization stages, incorporating more iron and other elements from the progressively enriched magma. South Pole-Aitken excavated through this stratification. The impact punched deep enough to reach the iron-rich lower crust, exposing materials that had been buried since the moon's formation. The excavated upper crust piled into the basin's rim, creating the elevated iron pore highlands that surround the depression. This is extraordinary. We're observing lunar formation processes directly, written in the composition of exposed rock layers. But there's a complication. Not all scientists agree that South Pole-Aitken exposed only crust. Computer simulations suggest the impact should have penetrated much deeper. For a basin this size, formed by a projectile perhaps 200 kilometers across, models predict excavation depths reaching 200 kilometers below the surface. That would breach the crust entirely, excavating mantle material from depths where olivine and pyroxene dominate. Yet we don't see strong olivine signatures in South Pole-Aitken spectroscopy. The basin floor shows elevated iron, yes, but the mineral assemblage still looks crustal. Crustal thickness maps from GRAIL confirm about 30 kilometers of crust beneath the basin floor, compared to 60 to 80 kilometers in surrounding regions. If the impact excavated 200 kilometers deep, where's the mantle material? Several explanations have been proposed. Perhaps the impact wasn't as deep as models predict. If the projectile struck at a shallow angle rather than vertically, it could have created a massive basin without penetrating to great depth. Low-angle impacts spread their energy laterally rather than driving downward. The basin's shape offers clues about impact trajectory. South Pole-Aitken isn't perfectly circular. It tapers toward the south, and topographic transitions are more gradual in that direction. This asymmetry suggests a southward impact trajectory, with the projectile approaching from the north at an oblique angle. Oblique impacts don't excavate as deeply as vertical ones. Energy that would drive downward in a head-on collision instead gets redirected laterally, creating a large but relatively shallow crater. This could explain why South Pole-Aitken is enormous in diameter but didn't breach the crust completely. Alternatively, maybe the impact did excavate mantle material, but that material isn't where we're looking. The most pristine ejecta from deep excavation wouldn't land on the basin floor. It would be thrown outward, deposited beyond the rim in rays and secondary crater fields. The basin floor, conversely, would contain a mixture of melted crust and debris that slumped back after the initial excavation. This might explain the crustal composition observed on the floor while still allowing for deep excavation. Recent mapping identified a thorium-rich deposit southwest of South Pole-Aitken. Thorium concentrates in creep materials, those late-stage magma ocean liquids enriched in incompatible elements. Finding thorium-rich ejecta southwest of the basin suggests the impact excavated deep enough to reach pockets of residual K-reap that had accumulated at the base of the crust or top of the mantle. This K-reap signature points to partial excavation of late-stage magma ocean materials. The impact occurred during a critical window in lunar evolution, when the magma ocean had mostly solidified, but pockets of residual liquid still existed at depth. Timing matters here. South Pole-Aitken formed 4.25 billion years ago. The Moon itself is 4.51 billion years old. That's a gap of only 260 million years. For geological timescales, that's rapid. The magma ocean may have taken 50 to 200 million years to crystallize completely. South Pole-Aitken could have struck when crystallization was advanced but not entirely finished, when dense ilmenite cumulates were sinking through the mantle and residual creep liquids were being squeezed into pockets between solid cumulate layers. Hitting the Moon during this transitional state would produce complex results. Some regions excavated would be fully solid cumulates. Others might tap residual liquid pockets. The resulting ejecta would show mixed signatures, exactly what we observe. This timeline also matters for understanding the lunar cataclysm hypothesis. For decades, scientists debated whether the inner solar system experienced a spike in impact rates around 3.9 billion years ago, called the Late Heavy Bombardment. Evidence came primarily from dating Apollo samples. Many rocks showed ages clustering around 3.9 billion years, interpreted as reset ages from major impacts during a bombardment spike. But South Pole-Aitken predates this window by 350 million years. If the Moon's largest basin formed before the supposed bombardment, that challenges the cataclysm narrative. Recent analysis suggests the clustering of ages around 3.9 billion years might be observational bias. Apollo missions sampled limited regions, many near Imbrium Basin, which formed around 3.9 billion years ago. That basin's ejecta blanket covers vast areas of the near side. Many 3.9 billion-year-old samples might simply be Imbrium impact products. South Pole-Aitken's age of 4.25 billion years provides crucial context. Major basin-forming impacts weren't confined to a narrow bombardment window. They occurred throughout the Moon's first billion years, with the rate declining over time as planetesimals were swept up or ejected from the inner solar system. The impact that created South Pole-Aitken represents the tail end of planetary accretion. It struck when the Moon was geologically young but no longer molten. The impactor was probably one of the last large planetesimals in Earth-Moon space, its orbit eventually intersecting the Moon's with catastrophic results. After the impact, South Pole-Aitken became a topographic low, a massive depression that would influence lunar evolution for billions of years. Volcanic magma, when it eventually formed deep in the mantle, found easier pathways to the surface through the thinned crust beneath the basin. This explains the volcanic plains within South Pole-Aitken, though they're limited. Magma preferentially erupted where the crust was thinnest. The basin's floor, with only 30 kilometers of crust instead of the typical 50 to 80 kilometers elsewhere, provided such pathways. But volcanism within South Pole-Aitken was never as extensive as on the near side. Why? The answer connects to the crustal dichotomy we discussed earlier. The near side's thinner crust made volcanic eruptions easier. Heat-producing elements concentrated in the Procellarum creep terrain kept the near side mantle warmer longer, promoting prolonged volcanic activity. The far side, with its thicker crust and lack of creep enrichment, experienced less volcanism. Even within South Pole-Aitken, where the crust was locally thinned by impact, volcanic activity remained muted compared to near-side Maria. Chang'e-6's volcanic samples tell this story. The basalts are ancient, 2.8 billion years old for most fragments. One fragment dates to 4.2 billion years, making it among the oldest lunar volcanic rocks ever sampled. These ages indicate that far-side volcanism occurred early and ceased relatively quickly. The mantle beneath the far side didn't stay hot enough to sustain prolonged melting. By 2 to 3 billion years ago, volcanic activity had essentially stopped. Contrast this with the near side, where volcanism continued sporadically until just 120 million years ago in some regions. The thermal evolution diverged dramatically between hemispheres. Space weathering adds another layer to the story. Samples from the lunar far side show different weathering characteristics than near-side materials. The Moon has no atmosphere and no magnetic field. Solar wind particles, cosmic rays, and micrometeorite impacts constantly bombard the surface, altering rock chemistry and texture over time. This process, called space weathering, affects all airless bodies, but Earth's magnetic field provides partial protection to the lunar near side. Once per month, as the Moon orbits Earth, the near side passes through Earth's magnetotail, a region where Earth's magnetic field extends downstream from the Sun. During this passage, the near side is shielded from solar wind. Particles that would normally impact the surface are deflected by Earth's magnetic field. This reduces weathering rates on the near side compared to the far side. The far side never enters Earth's magnetotail. It receives continuous solar wind bombardment month after month for billions of years. Chang'e-6 samples reflect this difference. Far-side samples lack certain vapor deposition layers found on near-side rocks. They show thinner amorphized rims on mineral grains. Solar flare track densities are lower. Nanophase metallic iron particles, which form from solar wind reduction of iron-bearing minerals, are larger but less numerous. These subtle differences reveal the environmental contrast between hemispheres. The Moon's two faces experience different space weather, leaving distinct signatures in surface materials. Understanding these weathering differences matters for future exploration. As humans return to the Moon, we'll need to account for environmental variations. Radiation exposure, dust behavior, resource extraction techniques all may differ between near and far sides. The far side, lacking Earth's protective magnetotail, presents harsher radiation conditions. Astronauts working there will need enhanced shielding. Equipment will face more intense weathering. But the far side also offers unique opportunities. Radio astronomy, for instance, could flourish on the lunar far side. Earth's radio noise, from television, radio, communications satellites, all the electromagnetic chatter of technological civilization, doesn't reach there. The Moon itself blocks it, creating a radio quiet zone unlike anywhere accessible in near-Earth space. Astronomers have long dreamed of placing radio telescopes on the far side. They could observe frequencies impossible to detect from Earth, studying the cosmic dark ages before the first stars formed, mapping the universe's large-scale structure through 21-centimeter hydrogen emission, searching for faint signals from the early universe. Communication challenges delayed this dream for decades. Without relay satellites, far-side installations couldn't send data to Earth. Chang'e-4 solved this problem in 2019 with the Queqiao relay satellite, Positioned at the Earth-Moon L2 Lagrange point, where it maintains constant line of sight with both Earth and the far side. This relay architecture enabled Chang'e-4's landing in Von Karman crater within South Pole-Aitken basin. The Yutu-2 rover has operated there for over 5 years, studying far-side geology and testing technologies for future exploration. Artemis missions will continue this work. Proposed landing sites near the lunar South Pole sit on South Pole-Aitken's rim, on ejecta deposits from the basin-forming impact. Astronauts will walk on material thrown from depths of tens of kilometers, sampling the Moon's ancient interior brought to the surface by violence 4 billion years ago. They'll collect rocks that may contain traces of the Moon's mantle, brought up from depths we've never sampled before. These materials could answer fundamental questions about planetary formation. How do rocky worlds differentiate into core, mantle, and crust? What processes dominated the early solar system? The far side holds these answers, preserved in stone for 4 billion years. Future missions will expand this exploration. Chang'e-7, scheduled for launch in 2026, will survey the South Polar region for water ice and other resources. Where exactly does ice accumulate in permanently shadowed craters? How much is there? What form does it take? These questions matter not just for science, but for establishing sustained human presence. Water means life support, breathable oxygen, rocket fuel. Finding it on the Moon changes everything about future exploration architecture. Chang'e-8, planned for 2028, will test resource utilization technologies. Can we extract oxygen from lunar regolith, manufacture building materials from local rock, 3D print structures using lunar dust? These experiments will demonstrate whether the Moon can support permanent settlements, or whether every supply must come from Earth at enormous cost. The far side becomes a testing ground for technologies needed throughout the solar system. International collaboration drives these efforts forward. China has invited scientists worldwide to study Chang'e-6 samples. Research teams from Europe, America, Asia, and beyond are analyzing these materials, bringing diverse expertise to common questions. Professor Mahesh Anand from Britain's Open University noted that Chang'e-6 findings are turning many well-established hypotheses and theories in lunar science upside down. International cooperation accelerates discovery in ways no single nation could achieve alone. This collaboration model may define future exploration. Rather than competing space races, nations increasingly share data, coordinate missions, and pool resources. The Artemis Accords, signed by over 30 countries, establish principles for peaceful lunar exploration, transparency, interoperability, emergency assistance. These commitments create framework for sustainable exploration benefiting all humanity. The far side becomes common ground, literally and figuratively. Yet significant mysteries remain. That massive anomaly beneath South Pole-Aitken basin, what exactly is it? GRAIL data revealed its existence, a concentration of dense material 5 times larger than Hawaii's Big Island, dragging the basin floor down by more than half a mile. Is it the metallic core of the impactor that created the basin, still embedded in the Moon's mantle, or something else entirely? The anomaly extends to depths exceeding 300 kilometers, far deeper than we can drill with current technology. Future geophysical surveys may reveal its true nature, but for now, it remains one of the Moon's deepest secrets. The origin of the near-side-far side dichotomy also puzzles researchers. Why are the hemispheres so different? Several theories compete for acceptance. Perhaps two moons once orbited Earth and merged early in lunar history, adding extra crust to one side. Or maybe a large object, a dwarf planet perhaps, collided with the young moon at relatively low speed, depositing material that buried the far side's primordial surface. GRAIL detected that extra crustal thickness, 3 to 6 miles of additional material on the far side, but determining how it got there requires more data. Heat distribution may explain the volcanic asymmetry. The near side crystallized more slowly than the far side, potentially accumulating more heat-producing radioactive elements like potassium and thorium. These elements concentrated in the Procellarum creep terrain, that compositional anomaly covering much of the near side. Their radioactive decay would have lowered mantle melting temperatures, producing vastly more magma beneath the near side than the far side. Laboratory experiments support this mechanism, suggesting the near side mantle could generate 4 to 13 times more volcanic material. But the full story likely involves multiple factors working together in ways we're only beginning to understand. The timing of South Pole-Aitken's formation remains debated. Different dating methods yield slightly different ages. Chinese scientists analyzing Chang'e-6 norites determined the basin formed 4.25 billion years ago. Other researchers, studying lunar meteorite Northwest Africa 2995, calculated ages between 4.32 and 4.33 billion years. These differences may reflect measurement uncertainties, or they may indicate we're dating different aspects of the impact event. The initial impact, the cooling of melt sheets, the final solidification of ejecta. Each process occurred at different times, potentially leaving distinct isotopic signatures. Understanding this timeline matters because South Pole-Aitken formed during a pivotal epoch. The Moon's magma ocean was crystallizing, creating the layered interior structure we observe today. Heavy bombardment pummeled all inner solar system bodies, reshaping planetary surfaces and possibly delivering water and organic compounds to Earth. South Pole-Aitken's impact occurred at this critical juncture, potentially excavating late-stage magma ocean liquids and mixing them with impact melt. Chang'e-6 norites show evidence of exactly this process. Crystallization from impact melt sheets containing materials from various depths. Each sample tells part of this violent story. The impact trajectory has been re-examined. Earlier models assumed a northward impact, but recent analysis suggests the opposite. The basin's outline tapers toward the south, and topographic transitions are more gradual in that direction. A southward trajectory would produce these features. It would also explain the thorium-rich, iron-rich ejecta deposit southwest of the basin, material from deep in the crust or shallow mantle, thrown downrange by the impact. This seemingly technical detail actually reveals fundamental aspects of how giant impacts reshape planetary bodies. Excavation depth remains uncertain. Simulations suggest near-vertical impacts should dig to 200 kilometers depth, potentially exposing mantle material. Yet observations don't clearly show mantle composition on the basin floor. Crustal thickness maps indicate about 10 kilometers of crust beneath the basin, less than the 50-kilometer global average, but still substantial. Perhaps the impact wasn't vertical. A low-angle impact by a 200-kilometer projectile hitting at 30 degrees or less would create the observed basin without penetrating as deeply. This scenario fits some data better than traditional high-velocity vertical impacts. These competing hypotheses illustrate how far-side exploration challenges our understanding. Every answer raises new questions. Every sample suggests alternative interpretations. This is science at its frontiers, where certainty gives way to probability, where models compete for explanatory power, where the next measurement might overturn decades of theory. The far side forces us to question assumptions, refine methods, embrace uncertainty as the path to knowledge. Human observers add unique value to this process. When Artemis II astronauts viewed the far side in April 2026, they spent 7 hours photographing and documenting surface features. Their observations included unexpected details: brown and green hues on the near side, smaller craters appearing unusually bright, like lampshade with tiny pinprick holes. As astronaut Koch described them, these subjective human observations complement robotic measurements, providing context and intuition machines cannot replicate. The astronauts also experienced something profound. During their far-side passage, they witnessed a solar eclipse from behind the moon, totality lasting about an hour. They saw Mars, Venus, Saturn alongside stars, Earth's faint glow and wispy corona baby hairs at the lunar disk's edge. But more than visual spectacle, the experience changed them. Koch reflected that viewing Earth from lunar distance reminded the crew how much we have in common, that everything we need Earth provides, which is somewhat of a miracle. This perspective, seeing our world as others have, fragile and precious against the cosmic dark, may be exploration's most valuable product. 24 humans have seen the far side directly. The Apollo crews who orbited the moon between 1968 and 1972, and now the Artemis II astronauts. Each described it differently. William Anders called it a sandpile kids have played in for some time, all beat up with no definition, just bumps and holes. Others found beauty in the desolation, meaning in the ancient cratered highlands. These varied responses reflect how exploration is ultimately a human endeavor, filtered through individual perception and experience. Yet for decades, far-side exploration seemed impossible. Harrison Schmitt, geologist, astronaut, and last person to walk on the moon, lobbied aggressively for Apollo 17 to land in Tsiolkovsky crater on the far side. His ambitious plan included a relay satellite at the L2 Lagrange point to maintain communications during descent and surface operations. NASA rejected the proposal as too risky, too expensive. The far side remained tantalizingly out of reach, visible but inaccessible, known but unexplored. Technology eventually solved the communication problem. China's Queqiao relay satellite, launched in 2018 and positioned at Earth-Moon L2, provides continuous line of sight between Earth and the far side. This architecture enabled Chang'e-4's landing in Von Karman crater, where the Yutu-2 rover has operated for over 5 years, studying far-side geology and demonstrating long-duration surface operations. Queqiao proved the relay concept works, paving the way for future missions. The far side offers advantages beyond geology. Radio astronomers have long dreamed of placing telescopes there, shielded from Earth's electromagnetic interference by the moon itself. Every radio transmission, every television broadcast, every satellite communication creates noise that obscures faint cosmic signals. The far side experiences none of this. It's the quietest radio environment accessible to humanity, perfect for observing frequencies impossible to detect from Earth. What could we discover with far-side radio telescopes? They could study the cosmic dark ages before the first stars formed, mapping the universe through neutral hydrogen emission. They could detect gravitational wave backgrounds from the early universe, signals too faint for Earth-based instruments. They could search for technosignatures, evidence of other technological civilizations, broadcasting across interstellar distances. The far side becomes a window on cosmos we've never clearly seen. These possibilities drive current planning. Future missions will scout locations for radio telescope arrays, test deployment technologies, demonstrate science operations in the far side environment. The moon transitions from destination to platform, from place to visit into place to work, to build, to establish permanent presence. The far side, once the most remote location humans could imagine, becomes the next frontier. This transformation reflects broader patterns in exploration history. Remote regions, polar ice caps, ocean depths, mountain summits follow similar trajectories. First contact and mapping, then scientific expeditions retrieving samples, eventually sustained presence, permanent stations, regular operations. The far side has entered this middle phase between initial reconnaissance and full utilization. What comes next depends on choices we make today. Resource questions loom large. Water ice in polar cold traps could support human crews and fuel spacecraft. Rare earth elements in impact ejector might enable local manufacturing. Solar power in regions receiving near constant sunlight could provide energy for expanding operations. The far side isn't just scientifically interesting, it's potentially useful in ways that justify the enormous costs of lunar exploration. But utility shouldn't overshadow wonder. The far side remains one of the strangest, most ancient, most scientifically valuable places humans can reach. Every rock tells billion-year stories. Every crater preserves solar system history. Every sample contains clues about planetary formation, cosmic bombardment, the processes that made rocky worlds possible. Understanding the far side means understanding how Earth itself came to be. We stand at a remarkable moment. Robotic explorers have returned far side samples for the first time. Human crews have viewed the entire lunar far side directly. Future missions will land astronauts on South Pole-Aitken's rim, walking on material from the moon's deepest interior. International collaboration expands access and accelerates discovery. Technologies mature that enable sustained presence. The far side, hidden for all of human history until 1959, now reveals itself through an unprecedented convergence of capability and curiosity. What we learn there will shape humanity's relationship with the cosmos for generations to come. The far side isn't finished telling its story. Every sample analyzed reveals something unexpected. Every measurement challenges previous assumptions. The Chang'e-6 materials continue yielding discoveries that force scientists to reconsider theories built over decades. Professor Anand wasn't exaggerating when he said these findings are turning lunar science upside down. The 4.2 billion-year-old basalt fragment alone extends volcanic history by over 1 billion years beyond what models predicted. The norites crystallized from impact melt containing meteoritic metals proved the South Pole-Aitken collision was even more violent and complex than simulations suggested. The space weathering differences between hemispheres demonstrate that even processes we thought we understood operate differently than expected. This pattern will continue. Future missions will return more samples from different locations within the basin. Each new site samples different depths of excavation, different impact melt compositions, different volcanic episodes. The South Pole-Aitken basin is so vast that we could conduct 100 sample return missions and still not fully characterize its diversity. Every rock tells a different part of the story. Every measurement adds another constraint to our models. The Artemis program will accelerate this process. When astronauts land on the basin's rim in coming years, they'll collect samples that no robotic mission could reach. They'll make field observations that cameras cannot capture. They'll recognize context that matters for interpreting laboratory measurements back on Earth. Human exploration and robotic sample return complement each other, each enabling discoveries the other cannot achieve alone. But the far side's significance extends beyond lunar science. It's teaching us how to explore other worlds. The techniques developed for far-side communications work anywhere line of sight to Earth is blocked. The resource utilization technologies being tested will be needed on Mars, on asteroids, throughout the solar system. The international collaboration frameworks prove that peaceful cooperation can overcome technical and political obstacles. The far side becomes a proving ground for humanity's expansion into space. Those mass anomalies beneath impact basins likely exist on other worlds too. Mercury, Mars, even Earth probably harbor similar buried structures from ancient collisions. Understanding what South Pole-Aitken's anomaly actually is will help us interpret similar features elsewhere. Is it metallic impactor material? Dense mantle cumulates? Some combination we haven't considered? The answer matters for planetary science broadly, not just lunar studies. The volcanic history revealed by Chang'e-6 samples challenges our understanding of how rocky worlds cool and evolve. If the far side remained volcanically active billions longer than expected, what does that imply for other planets? Mars shows ancient volcanic plains, but also relatively young lava flows. Mercury has volcanic features that don't fit simple thermal evolution models. The Moon's two hemispheres followed different thermal trajectories despite being part of the same body. This complexity may be normal, not exceptional. Space weathering differences between near and far sides matter for interpreting remote sensing data from asteroids, Mercury, Mars. Any airless body where solar wind bombardment shapes surface properties. We can't assume weathering rates are uniform. We have to account for magnetic field protection, orbital geometry, solar distance. The Moon teaches us what to look for elsewhere. These lessons accumulate slowly. Decades of lunar exploration have revealed how little we actually understood despite centuries of telescopic observation. The far side's very existence remained unknown until spacecraft could photograph it. Its composition stayed mysterious until samples returned. Its internal structure emerged only through gravity mapping. Its volcanic history required precise radiometric dating of returned materials. Each capability unlocked new knowledge that raised new questions. The process continues. Seismic networks will reveal the Moon's deep interior.